I'm Ryan, as Jane just mentioned, and I'm going to start talking this evening. So just to start off, I want to say good evening. My name's Ryan, and this is my colleague Oscar, who you'll hear from shortly. And we're very honoured to be invited here to speak to you about lean design and structural innovation. We both work for the thriving consultancy Civic Engineers. For those that don't know, we're a multidisciplinary engineering firm. We have a keen focus on structures, streets and places. I'm sure most of you on the call are as well, but our primary focus is for our designs to have a positive impact on the environment, whilst also enabling people to lead healthier and happier lives. So why do we need to adopt lean design and how do we do it? Our aim this evening is to hopefully spark a few ideas for as to what lean design is and how we as structural engineers can use it to help the environment. We'll also be touching on some approaches to structural innovation too, which Oscar's going to touch on towards the end of the lecture. So the quick overview of what we're going to cover, I'll give you a quick background to embodied carbon and why it's so important. I'm going to talk a little bit about challenging the brief. I'll touch on retrofit and reuse, and Oscar's also going to talk about sort of reusing steelwork, but then we'll go on to talk about applying modern computational methods and investigating novel materials and products, all with sort of embodied carbon and carbon in the back of our minds. So what's the primary aim? The primary aim is to reduce carbon. There's really no need for us to tell you about why we need to cut out carbon. There's an increasingly terrifying amount of information out there about how the direction the climate's headed in, although perhaps not always making the headlines as it should. As engineers, we're in a unique position to influence the future. To get serious about reaching net zero carbon emissions by 2050, we need to take serious action. We can't build our way out of this. The best way to reduce our impact on the environment, particularly with respect to the embodied carbon, is to simply use less resources, less carbon, less energy. And I'm hoping everyone on the call will agree, but it's necessary from an ethical standpoint, but also various others as well. So why don't we just stop building? You know, it's easy, we just stop building things. Well, we have a lot of buildings already, but the world changes, demands shift, and downing tools isn't exactly really sort of economic or, well, it's not a realistic option, but taking what with that is. So conservation of energy and carbon is now absolutely vital to keep global emissions down. We're at a critical point, and I'm sure everyone can agree. A massive amount of the global carbon emissions are created by the construction industry. 10% of the UK's emissions are directly associated with construction, and embodied carbon will be responsible for almost half of total new construction emissions between now and 2050. So that gives you a bit of a bit of a background to why this lecture is so important and why we need to be focusing on embodied carbon and carbon at the forefront of our designs and the forefront of structural engineering. I'm sure a lot of you are aware, but there's an increasing number of industry targets to achieve for embodied carbon in designs and in buildings and all the rest of it. Leti have set out a series of embodied carbon reduction targets, which are outlined on this slide, and I should add that these targets are for the upfront embodied carbon, sort of A1 to A5. So just bearing that in mind, on the next slide, as structural engineers, what can we do? And that's the big question sort of tonight, and that's a big question in general. This graph I pulled together, and it shows a split of where we currently sit, or where I think we currently sit on average, for what percentage of the upfront carbon is associated with various building elements. So as it stands, for a new build, the structure typically on average contributes around 50% of the embodied carbon, with services, facade, windows and other various bits and pieces making up the other 50%. So to reach 2030 targets and beyond, ones I just spoke about, how do you envisage the split being? Do you envisage the split being the same? It'd be really good to get everyone's views on it, and so I've made a poll, which hopefully is going to work, but I will ask it now. So I've just asked everyone a poll, and I think you should be able to give an answer to that. I think if you close the poll, you might not be able to have another go answering it, so give it a go. But I'm going to touch back on this at the end, and I'm going to have a look at the results at the end, but it's just be interested to know that where do you think the structure is going to sit in this pie chart to reach 2030 targets? That's the question. So moving on. So the first aspect of lean design that I want to touch on is challenging the brief. And this includes interrogating serviceability criteria as well. We need to be safe in our designs, and we need to be designing to code, but that doesn't mean we can't be challenging the design at the same time. So the Abstract T publication, the Circular Economy and Reuse Guide is really, really good. Download it if you've never seen it. Should be followed, definitely, and is very, very good for all of this information. But as an environmentally conscious engineer, and as environmentally conscious engineers, we need to be challenging client requirements where it's safe to do so, and where the code permits us to do so. So that brings me on to this. So where can we challenge the brief? So within sort of the facade and internal partitions, are the facade contractors' limits realistic, and are they based on actual conditions, or are they generic, and can they be challenged? I'm sure a lot of you on the call have found that designing to strict deflection limits is tough, and it means you make your structure a lot larger. You end up doing things to bring them down, but we need to challenge them. And with partitions, can larger deflection heads and vertical joints be used as standard? Is that something that we can do? It's conversations we need to be having. For long spanning beams and sort of beam deflections, if deflection is governing the design, then, which it often does, then why don't we look at pre-cambering or using a lower strength material? But also we should need to be looking at whether the connections on either end are fixed, pinned, or somewhere in between, because it's all going to contribute to the beam and the sort of the design of the beam itself. Vibration is quite a big one. So with vibration, are the limits set? Are they appropriate for the intended use of the building or of the floor? Or could some localized exceedance be accepted? We typically design vibration for low imposed loads using a factor of around 0.1, which is extremely conservative, and it often means that there's only around 10% of the live load on the floor plate. Question to ask is this reasonable? Does it really matter if the only person experiencing a bit of vibration is the first person in the office at 7 a.m. in the morning, when there's hardly any live load applied to the floor plate? Adding mass to a structure to keep localized vibration down is a carbon-intensive way of doing things. It's something we need to be challenging. It's vital that we have these discussions with the client, and the client's aware of anything that challenges normal design, but it doesn't mean that we can't challenge them in the first place and bring up the discussion early on. The final thing I want to touch on is reducing material safety factors, and that's something Oscar's going to touch on towards the end of the presentation. So next thing, and there's a big topic, but it's retrofit. I personally think that the leanest design is a design that uses less material. So with that in mind, what is retrofit? Retrofit is a word that is used a lot in our industry at the moment. But what does it actually mean? It simply means adapting, modernizing, and changing. Retrofit isn't just what we have and adapting it to suit our needs better. It implies a more technological change than renovation, but it isn't a new idea. Reusing old stuff isn't crazy. Reusing old buildings isn't a new idea. If you walk along any row of theoretically identical terraced Victorian houses, if you live in London, you'll know exactly what I mean. And you'll see loft extensions, rear extensions, walls that have been knocked down, new windows, and so on. As builders, we've always adapted our environments better suit our needs. It's not something that we need to be scared of. It's not a big, scary new way of thinking. And I want to use the next couple of slides to show that as engineers and designers, we already have the skills to do this. It's not a radical idea in many ways, but the application of it and sort of actually doing it, the result of it can be dramatic. So I want to talk to you a little bit about a case study. This is Cannon Green in London. This is the before picture and after picture. It's a concrete frame building, and I'm going to refer to it on the next slide as well. But What we did here is we added a couple of stories, added a roof terrace to the top, changed the use of the basements and the ground floor, added a bar and gym, and we also constructed a new sort of wraparound podium as well. This is a bit of a sketch for what we did. It is a very sort of high-level overview of it, but changing the use for a building or the shape of a building may change loads, load paths, building height, stability, and so on. The first step and the most important step is to really understand the building you're working with. Undertake a really solid feasibility study. It needs to be carried out to gather as much information as possible. And the appraisal of the existing structure is your friend, basically. The key to understanding and unlocking a building's potential is to unpick and understand how the loads travel down through the building and into the foundations, both in the existing case and the proposed case, as you can see here. Buildings need to be understood holistically, and it's pretty typical for buildings to have gone through previous lives. Columns might have been removed to open up areas, extend doorways, staircases might have been taken out or added in, lifts might have been moved. So it's very important to understand the building. Original engineering or construction drawings, if you get lucky and find them, they only tell a snapshot in time, and it's really important as an engineer to validate any drawings and any assumptions on site. So with the frame and the load path understood, a load takedown can then be carried out, which is the baseline for all future assessments of capacity and change. And that gives you a bit of a background about sort of how to work with existing buildings. The iStruct have a fantastic comprehensive step-by-step guide for structural engineers needing to check and report on the adequacy of an existing building or an existing structure even. And if you're ever working on existing structures, this guide is your best friend, and it covers sort of everything from stability to strength to dynamic responses and durability. Again, it's another document I'd recommend downloading. So once we understand the existing building, the simplest way to justify any addition to the building or any sort of changes to the building is load balancing. If the proposals don't add load to a given structural element, or they don't sort of change that element in too many ways, then by observation it's okay. Existing loads like heavy screeds and partitions can be removed. The change of use going from a warehouse, for instance, with really high storage imposed loads and machine loads to a residential use might release sort of 2 to 5 kilonewtons per meter squared of live load, which when you multiply up through the building, that's a lot of dead load. That's a lot of load that can be added into the columns and into the foundations, especially if you're going to be using a light method of building on top. So that's key to understanding what, the capacity of the building, what could be done. If you get lucky, you might have the loading allowances on old drawings, or you might find them on a plaque on a building somewhere. If not, you need to be understanding the time that the building was designed. You need to be understanding the codes and the live loads that they might have used, and working with knowledge and how existing buildings were designed and constructed in the past. And this graph sort of outlines how imposed loads have been applied over the last 100 or so years. Then, dating back to the early 1900s, chances are, if your building was constructed then, it might have been built with higher live loads than it would be now, and therefore you might have some residual capacity in the structure already. The majority of the time, retrofitting a building will mean a change of load path or increase in load, at least to some aspects. You might end up strengthening foundations, columns, beams, slabs, something like that. But the result is a brand new building that's got an old building at its core. This massively reduces the need for new material. It reduces the wastage of any old material, and it hugely reduces the overall embodied carbon on the new structure. And I'd like to think that this is sort of lean design at its absolute best. So the next thing I'm going to touch on is donor buildings, which I only actually heard the term donor buildings about 6 months ago. And also we're going to touch on steelwork reuse, but I'll talk about donor buildings first. So going back to retrofit, you can't always build up or out of an existing building. And you might be working with a completely empty plot of land, for instance. And with an empty plot of land, you've got a lot of options. There's a lot there's a lot of possibilities. But if you're building a new building, you need to make sure and work hard that it's a low carbon design, which we'll come on to. But one of the first things you should do is ask, are there any buildings that we can mine material from? Maybe there's a site nearby. Maybe one of your clients got another project somewhere where you could sort of mine some material from. Are they getting rid of any steel work? Or are some of your colleagues working on existing buildings, and are they removing any old steel work, masonry, precast concrete, timber rafters, anything like that? These are questions we need to be asking ourselves, especially when we're talking about new buildings. And I could go on a lot of detail. I could go into a lot of detail about this, but I won't, because it's we haven't got too long, and I want to cover a few other items. But I will touch on a case study, and then I'm going to pass on to Oscar, who's going to talk more about reusing steelwork. So I'm sure many of you are aware of how steelwork's made. In the UK, generally, up until now, we've used blast furnace steelwork, although we do use electric arc furnace steelwork, which is much less carbon intensive. We just don't. I think we don't have any arc furnace or electric arc furnaces in the UK, or we didn't until recently. I think there will be one soon, or someone's just constructed one. But anyway, historically, we haven't. And when we do use it, typically we've sort of done it abroad and then transported it in. But this brings us on to the next slide, which is a graph showing the embodied carbon of different steel manufacturing routes. So blast furnace, which is typical for UK, very carbon intensive, at about 2.5 tons of embodied carbon per ton of material, or per ton of concrete produced. Steel produced even. UK average a bit lower because we do between blast furnace and electric arc furnace. Electric arc furnace being much lower, about 0.5 ton of embodied CO2. X-carb, for anyone that is not aware, is an Arcelor metal product. I don't know if I pronounced that right, but it's an Arcelor metal product, which is similar to electric arc furnace, but it uses renewable energy to help power the process. So it's very low carbon intensive, not very carbon intensive. However, what I really want to point you to is reused steelwork. So if you're constructing, a building, or at least part of a building, out of reused steelwork, as opposed to, any of these other forms, your embodied carbon is tiny compared to the rest of it, and it's something we should be looking at where we can, all the time. Anytime you're installing steelwork, think, is there any steel that we can reuse? So I'm going to talk to you briefly about another case study, which is 318 Oxford Street in London. It's a 1930s steel frame, going over it very quickly. It was a bit of a big retrofit. I was about to say a bit of a retrofit, but it's a big retrofit where we've essentially removed part of the structure, which you see here in red, added 3 more stories, and constructed some new structure in between, and a new core's gone up to act as the stability system and the rest of it. But what this means is that all of this removed steelwork, there's a chance for all this removed steelwork to be reused, and so we did, which I'll come on to. This is a picture of 318 Oxford Street being constructed. On the left, you see all the steelwork going in, and very nice picture. And this is a picture of some really safe construction methods, also on 318 Oxford Street, but I don't think we're doing that today. So this is what we did. So some of the structure that you can see here in orange and green was removed and reused on another site in London. It's now constructed, so it's sort of living proof that it could be done. It has been done, and the way it was done, Oscar's sort of going to touch on it in a second, but essentially the steelwork was removed from the building, stored on site, taken away, tested, refabricated where needed to be, cleaned up, and then installed on another site in London elsewhere. So what worked with this? It was identifying the opportunity early. It was, it was being on site, noticing all the steel and sort of saying, right, there's a lot of it here. We're going to be taking a lot out. It's big sections. We should be reusing it. getting the client involved and making sure that having client support was vital, because at the end of the day, you need, for something like this, you need to have sign off. You need to get it signed off. It was visually appealing steelwork as well, so it wasn't like it needed, it didn't need too much work. It looks good. So after talking with contractors, engineers, clients, getting everyone involved, it was something that worked, and has worked very well. So what didn't work about this was the sort of nervousness around 1930s steel. It's almost 100 years old, it's about 90 years old. People saying it's too difficult. Although it was sort of appealing, it looked appealing, the steelwork, there was a lot of plated sections. Some of the sections they had back then weren't big enough, so they ended up just sort of riveting plates onto it to make them stronger. This made it really difficult to reuse, especially as beams. For instance, how would you add metal decking, or how would you sit metal decking on top of a section that fluctuates by a couple of 100 mil? It's tough. So there were things that struggled, but it worked, and it's just living proof that it can be done. But I will pass you over to Oscar, who's going to talk to you more about the guidance on reusing steelwork and talk to you more technically about it.
So I'll just take over now and discuss a little bit of the technical side as to how we can reuse steel from the past. The first bit of guidance that's been introduced quite recently is by the SCI. It's P427, and this covers steel that's been constructed since the 1970s. This is kind of the first port of call that engineers should be looking at when looking to assess previously constructed steelwork that they'd like to reuse. I just want to emphasize the difference between reuse and recycle, actually. So recycled steel would be where the steel is melted down and reformed into rolled sections, where what we're looking at here is actually dismantling structures, trying to save as much as possible and just forming new connections. So just going back to this guidance, this was introduced quite recently. And what it basically sets out is a series of checks and tests that are needed in order to understand what the material qualities are of the steelwork in order for us to be satisfied that it's up to scratch and up to the requirements of modern methods of construction. Now, 1970 steelwork, being able to use that is great, but obviously there's a lot of building stock that's been introduced before that that also could be utilised, like it has been on 418 Oxford Street. It's worth noting, actually, that this guidance has only been introduced recently, and the work we've done on 318 Oxford Street, we didn't have the benefit of this guidance. And what we actually did is we created a series of processes in order to understand and satisfy ourselves that the steel that we were reusing was acceptable. But this guidance is particularly useful because it allows for steelwork to be CE marked, which allows for steelwork to be sold and bought on the open market. Now, because we weren't selling or buying on the open market, we didn't need that CE stamp of approval, which is why we weren't relying on this guidance. The way that the guidance works, I've gone through, but there is a couple of limitations as to how we can use this. So the consequent class of the structures that you are using this material for can only be class 1 and 2. It also doesn't cover built-up members. So like Ryan mentioned, typically in the past, you'd have some form of basic rolled section that's then augmented with plated members. That isn't covered by this guidance. It's also important that we don't use steel from structures that have been subjected to fatigue loading. So things like bridges wouldn't be suitable for reuse. And likewise, we cannot then apply this material to structures that will be subjected to fatigue loading as well as seismic loading. So for steelwork before 1970, we've already had a supplement that's been provided by the SCI, and this essentially provides some additional checks and tests in addition to what's been set out by P427. I'm not going to go through the details of this just so we can cover as many different opportunities and exploits in terms of lean design and reducing embodied carbon, but you should be able to get hold of these guides and read through them in detail to understand how you can apply it to one of your projects. The next thing I'd like to discuss is the load testing of piles. Now, this is quite a common practice already in the industry, but it's worth touching on just because of the real tangible benefits that you can get from using load testing in piles. And the reason being is that when you load test piles, it does give you access potentially to lower factors of safety that you can take when designing your piled substructures. So if you were to just use a phase 2 site investigation, if you look at the table on the right, that central column is the factors of safety that you would have to work to. Whilst the right-hand column, if you do static load testing, you can actually reduce those down. The stipulation is that 1% of the piles are needed to be static load tested, but if you meet those requirements, you can use lower factors of safety. The reason being is you're essentially gathering a higher resolution of information about the grounds and the piles that are being installed than you would with a more broad brush phase 2 approach. So it's all entirely safe and thought out. It's just you're getting more information, so you're able to get a leaner design. The way that this works is shown here. So if you look at the right-hand side diagram, this is a diagram of a typical testing setup. So the pile in the center, this red pile, that's the pile in question that we would be testing. And then the piles on the left and right in green, these are sacrificial piles. They'll be designed via skin friction, most likely. And the way that they work is this yellow gantry structure is anchored to the green piles, and then a hydraulic ram that's fixed to the top of the test pile in the center. It jacks against that gantry, which allows the load to be placed onto that red pile in the center to understand the displacement over time in relation to the magnitude of the force that's applied. On the left-hand side here, you can see a chart. This is actually some information that we received from a project that we've recently completed in terms of the pile testing. And what you can see here along the x-axis is the magnitude of load tested, and then on the y is the displacement of the pile. And what was done here was there was 3 sequential loading events where we loaded up, then loaded down the pile, and we did that in increasingly larger magnitudes. So you can see on the third set of loading, it reached 6 meganewtons, and we see that the final pile the displacement, it went from 25 mil under full load back down to 16 approximately mil, and that just shows the kind of the consolidation of the soil. You're not expecting to see that to go right back down to 0 once the loading's been taken off. So like I said, we did this on a previous project. We do this on quite a lot of projects, and I think the advice I'd give to everyone here is if you have the opportunity to do this, I would push for it and lobby with the client to get it done. So on the left-hand side is Mayfield Phase 1A. This is a project that both Ryan and I are involved in. Ryan's involved in the left-hand side office building, that's the Republic, and I'm involved in the Poulton, which is on the right-hand side. This is phase 1 of the Mayfield master plan. So it's a £1.5 billion redevelopment project for the client Landsec that's focused around this central park here, which was formed on previously disused brownfield land. Now, we had a bit of a time to play with, but we also had to make a meaningful start on site due to planning conditions. And that is where pile load testing is a particularly good benefit or a good option to take. So you can see on the right hand side, we've got this piling rig set up. It's a slightly different arrangement from what was shown in the previous diagram, whereby we have a number of additional reinforcement sections to the rig. And this is just in the process of being set up. So the benefit to this in terms of tangible explanation is that the pile diameters for the original scheme were designed to 750 millimeters, and based on the reduced factors of safety, we were able to drop that to 600 millimeters in diameter, which corresponds to approximately a 32% reduction in the embodied carbon and the volume of concrete in those piles. And when you take that when you compare that to the total share of embodied carbon for the whole scheme and the whole structure, these are really tangible benefits. I think just going on to the point of how we lobby this to the client, there's a good correlation between cost and embodied carbon in this situation, because we are simply looking at reducing material. Obviously, there's an initial capital cost with doing the works. You've got the mobilization cost, and they've got the time cost of bringing this equipment to site, piling, and then doing the testing. But when you have a project which has the program flex and it does have the scale, this is something which is quite often a very attractive strategy to employ. The next thing I'd like to discuss is applying modern computational methods to our designs. And this is something that I believe we can apply to much more than the large mega projects with super complex geometry. I feel like there is a place in quite a lot of different design situations for structural engineers now. So it's something that I quite enjoy investigating, and it's something I advise everyone gets an understanding of and an interest in. So on the right-hand side here, you can see this 3D plot, and I like to think of this as like a solution chart. And what you could say is the z-axis of the chart corresponds to something, say, like structural tonnage, and then the x and y axes would correspond to some of the design inputs that we as engineers have the ability to manipulate. So that might be section sizes or span or structural depth. There's numbers of different ones. Now, this is only showing 3 axes, so that would be an x and y, where would be your variables that you can control. But quite often in design situations, we have many more inputs and variables that we try to balance against each other to find the optimum design. And when you don't have a clear and obvious relationship between the combinations of design variables, so for example, going back to that, there's the example of say like a span length and structural depth, we can imagine that the relationship between structural tonnage and those two inputs is going to be fairly predictable. But you do have design situations where those combinations of inputs start to produce more irregular and hard to predict patterns in relation to the kind of the ideal solution. And this is what the chart on the right tries to show. This is where applying machine learning algorithms is particularly beneficial, in that if you can define your analytical problem in a parametric fashion. And what I mean by that is, instead of traditionally setting up your analytical model by manually drawing out the geometry by hand, instead of that, you actually create a parametric definition for the geometry where you can change the inputs, say structural depth and span length and things like that. You can then create a definition, a parametric definition that you can then link to a feedback loop and a machine learning script that the computer then takes control of. What that allows you to do is to send geometry to an analysis program, bring out the results of the analysis program, and then use those results as an input for some kind of machine learning algorithm that then can enforce and set up new iterations of analysis. When you multiply that up over loads of different iterations, you can quite often get some really unique and interesting solutions that would have been quite difficult to have found through traditional analytical methods, whereby you would be doing this by hand. So one of the examples that I've worked on myself is this sculpture here. This is in Wakefield, a place called Tileyard North, and it forms part of a wider regeneration project where we retrofit and refurbished a complex of derelict Victorian mills. What we did here was we wanted to create this central square and sculpture. You can see in the picture on the right hand side this masonry stack. That's the remnants of the original chimney that helped power the mills back in the early 20th century. It was truncated down by 2/3 back in the 80s. And what we wanted to do is we wanted to recreate that original silhouette, but with contemporary materiality that gave a nod to the past use of the site, but also reflected the modern use. And you can see the materiality of the circulation core just behind it. So it ties the whole site together on a aesthetic level. So what we wanted to do was we wanted to figure out how we could optimize the steelwork tonnage for this. And in order to do that, we actually defined the geometry of the chimney. We had certain constraints we had to work to instead of with regards to the base diameter and the height, but we also had a lot of parameters that we could play with. And that's how we set up the parametric script that I'll show you on the next slide. So on this slide, what you can see here on the bottom right is a grasshopper script, and this is the kind of the definition that allows us to define the geometry and then speak to the analysis package via this machine learning algorithm, which is set up via the Galapagos function within Grasshopper, which is an inbuilt function within Rhino 7. On the screen share, on the screenshot with the GIF on the top right, you can kind of see this process and is sped up. So the left-hand window is showing the analysis program going through different design options, assessing it against deflection. And then this central window here is that Galapagos interface that I mentioned previously. It's working through a solver plot to try and find the optimum combination of inputs to minimize the steelwork tonnage. Just going to touch on material innovation now. This first piece of material innovation is called concretine. Again, I've been very fortunate to be involved in this. This is essentially enhancing the material properties of concrete via impregnating it with graphene at the batch plant stage. The graphene is a two-dimensional material, and what that allows is you have these platelets of graphene that are kind of dispersed throughout the structure of the concrete slurry, and they then form this medium that allows the crystalline structure of the concrete to develop in a much more robust and structurally efficient manner compared to when you don't have that medium present within the concrete mix. The benefits that has is that as I said, the crystalline structure is much more robust. So this improves curing time, and we're finding that you can get compressive strength, 28-day compressive strength within 24 hours. And it also improves the compressive and tensile capacity of the concrete. So this could be compared to GGBS, whereby you reduce the cement content of a mix and still achieve the same concrete grade that you would want, but you also have the benefit of reducing that cement content, which is a massive component of embodied carbon, which is associated with concrete. This has similar benefits, but it also doesn't have the delaying effect on that curing time, which is often an issue when you're using GGBS in a concrete mix. There's also, like I said, benefits to the tensile capacity of the concrete when you use concretine. And although it's still early days, there's indications that you can reduce the amount of tensile reinforcement required in elements designed with concretine. Now, it's worth saying that it's currently looking like it's going to be viable around 2025. This is a work in progress, and the picture on the right is actually the first pour that we did. That was the first suspended slab globally with the use of concretine, which was essentially used as a large-scale test. We are monitoring how this is progressing, and it's looking very promising. The reason I wanted to raise this is because I feel like it's really important that engineers understand what's coming down the pipeline, so that we can support our industry partners, because they play a big role in allowing us access to materials that are going to help us minimize embodied carbon, but also to ensure that once these products are ready to go, we're aware of them and we can apply them in the manner that best utilizes their benefits. Another interesting innovation on concrete is carbon cure. This is quite popular in the US currently, and how this works is, in a nutshell, it's essentially sequestering waste CO2 into concrete in a way that actually improves the compressive capacity of the concrete. And this works by creating calcium carbonate by injecting waste CO2 at the bench plant, similar to GGBS or graphene. But the thing that's interesting about this is, because the carbon is now sequestered in a mineral form, I think there's a good argument to be made that when you're completing your embodied carbon calculations and comparisons, you can take this sequestered carbon as helping to reduce the embodied carbon of this proposal that you might be looking at using carbon cure. Well, comparing this to timber structures, I think the current guidance is that you do not consider sequestration for timber, carbon within the timber, when comparing it to other options. And that's because at the end of at decommission of the building, it's quite likely that the carbon stored within that timber is then in one way or another going to get out to the atmosphere, either through organic breakdown or burning of that timber, whilst that's not something that would occur when sequestering the carbon in this mineral form through carbon cure. So on to structural innovation products, there's the first one I'd like to discuss is the mini mass beam. This is really cool precast elements that's been developed recently, and this is based on the Truc de la Fare bridge you can see in France, shown on the bottom right. This works on the basis of a tension compression truss. The compression element of it is formed with 3D printed concrete, and then you have this cord of post-tensioning, which is situated within a duct. We've also researched recently the use of the Cree building system. This is something that's it was first created in Austria, and we looked at applying this in Mayfield to see if we could utilize the sustainability benefits of this this material, or this building product. The way that it works here is that you have a combination of glulam and concrete to form a modular construction method, whereby the system utilizes the benefits of the materials and to form something that comes together in a really efficient manner. So if you look at the downstand beam here, formed of concrete, that provides the bearing of the prefabricated modules that sit on the glulam columns. If you're familiar with timber design, you'll be aware that quite often the connections of timber can be quite tricky and quite cumbersome due to the localized shear capacity of timber connections. So using a concrete bearing is a good way of avoiding that, but it also provides a good fire stopping break between floors. That's the benefit of the concrete has been utilized in that sense. And then you've got the embodied carbon benefits of utilizing timber. So the timber is actually designed compositely with the concrete slab on top, and together it forms something that's quite program efficient and sustainable. You can see here, this is the one of the units being lifted into place. And I just wanted to basically touch and summarize these last two sections briefly, in that I've only taken a few options that we've researched and just looked to apply in our building designs over the last couple of years. But the lesson I want to kind of go through today is that these products, especially when you're speaking with representatives of these companies that are trying to sell these products, is you'll often be advised that this is the solution to whatever problem you're facing. And it's absolutely critical as engineers that we understand how buildings are put together, and we understand the implications of adopting some of these new products that essentially are being sold to us. So there is, without a doubt, really excellent applications of these products in design, but it ultimately is the responsibility of us as engineers to assess whether or not it's suitable in our specific designs. So as Ryan was mentioned earlier, we set out this poll, and it's based around what we believe that the future carbon split is likely to be of structures in 2030.
Yeah, so as Oscar just said at the beginning, I asked what percentage of upfront embodied carbon do you think is associated with the structure relative to other building elements in order to achieve future targets, and it was the poll that I put out. So I've just published that, so you should be able to see the results. And basically, it's obvious that we have an ever-increasing need to reduce embodied carbon in our designs as engineers. The focus on the industry has been on operational carbon for the last sort of 20, 30, 40 years. And there's not as many easy gains as it stands for operational carbon, such as MEP and building fabric, etc. So the focus is now more and more on the structure. And until others catch up, it's going to remain this way. So historically, the structure is made up of about 50% of a building's embodied carbon on average. Moving forward, it's obvious that we, sort of as structural engineers, need to work harder to bring that percentage down. It's not just a linear reduction on the current split, because there is just simply more opportunity, as we've just sort of explained in the presentation. There's more opportunity for us to reduce the carbon. It is a subject to debate. The graph on the right is not set in stone, and is why I asked the question, because I was intrigued as to what other people think. It's my interpretation, or it's our interpretation, that the structure needs to be down at around 35 to 40%, or even lower. So what that means is we need to be working really, really hard to reduce embodied carbon, so that there's a bit of wiggle room for the others to sort of be a little bit more carbon intensive, if that makes sense. And this is achievable assuming best practices are performed, and we adopt lean design, we challenge briefs, and we use our innovation to achieve low carbon designs. And that concludes what we wanted to speak about. So thank you very much for listening.